Lab 1, Constant Velocity, submitted by Robert Stewart, Georgia Tech Introductory Physics through Coursera. The objective was to observe an object moving at a constant velocity using tractor, then model the motion with Python using Newton's second law to compare the model and observation results. The device I used for my video study was a hovercraft-like puck called a kick disc. It was on a kitchen table with a tripod mounted on the table looking down on the puck as it was pushed across the table. The motion data from tracker was compared to the Python model. Here is the tracker screenshot showing the measuring stick overlaying the ruler for 10 centimeters, and the axis was rotated around and tilted. I used video frame 77 to 116. The calibration stick was 10 inches or 0.254 meters, and the kick disc traveled from right to left, so the coordinate axis was rotated to make right to left positive direction. And since the travel was not horizontal across the video frame, I rotated the axis so that the center of the disc always followed the axis line. The initial values for the Python model, taken from the tracker analysis, are shown on this screenshot. The velocity initially was 0.515 meters per second. Newton's second law says that the F net is equal to 0. The sum of all the forces is vectors, add to 0. Then that term F net divided by mass, which is the acceleration, will be 0, and the new velocity will be equal to the old velocity times 0 times change in time, which means the velocity should remain constant. The position is calculated in a similar fashion by taking the velocity, multiplying by the small time interval, and adding it to the last position. Since delta t is small, this is repeated with each v2 and r2 becoming the next v1 and r1 in the next iteration. The model builds the predicted motion one small step at a time. This screenshot shows the initialization of my Python model with the ball position vector and the ball initial velocity vector. The calculation loop is shown with the net force vector being set to 0 and the ball velocity calculation and the ball position calculation and the update of the time. The results of running the Lab 1 PY model is shown with the little ball representing the puck. It traveled to the right because I had rotated the axis around and defined that. I didn't know how to change that in the Python model. And then the graph showing the velocity positions at a constant velocity. Here is the spreadsheet of the two data, the observed data and the modeled position data, and they essentially overlap as shown. Here is a closer view of that screenshot. The first 10 data points are right in the center of the model position. They drift to the upper side of that bar. I did not know how to make that bar any thinner in Excel. It's on my to-do list to do. The agreement seems to be good, especially for the first 10 data points, but it seems, is it close enough? I think so. There is some uncertainty in specifying the center of the puck, so that may be the cause for that. Also, round off could be a concern in this model, I think, just asking. What if? How does the selection of the coordinate axis affect the results? The graph line shown would have been increasing negative positions. In other words, the line would have gone below the time axis, representing negative x values instead of positive x values. And if the axis was not rotated so the center of the puck always passed through the axis line, there would have been increasing y values, and that may have changed the value of the x velocity that was calculated. What does it mean? The net force of 0 does result in constant velocity. The close agreement supports this. But F net equals 0 does not mean no force, just that the vector sum of all the forces or interactions is 0, and no change in motion results. The forces acting are gravity and the supporting air cushion. Friction does not appear to be acting because there is no decrease in velocity observed. Some final thoughts. To determine how constant the velocity was, I calculated the average velocity over the whole 1.3 seconds of the tracker analysis, giving me a value of 0.513 meters per second compared to the 0.515 meters per second calculated in the first 2 data points. The average velocity over the entire time is less than 1% from the value calculated in the first 2 data points. Thank you, and this is the conclusion of my lab report.